So we already looked at graphing rational functions from transformation form. Now we're going to look at graphing some other rational functions. Graphing rationals isn't necessarily hard. It's just that there's a lot of parts that you need to think about. And those parts are vertical asymptotes, which we talked about in the transformation video, end behavior asymptotes, which we talked about in the transformation video as well. Vertical asymptotes are vertical lines where the graph veers off because those are things that make the denominator equal 0. And behavior asymptotes are usually horizontal, not always, but usually. And they also show where the graph veers off. In this case, it describes what happens at the ends of the graph. So the vertical asymptote is always vertical. The end behavior asymptote is generally horizontal. There are a couple other things that we need to graph when we graph our rational functions. We're not going to graph them perfectly by plotting every single point, but we're going to use information that we can find relatively easily and then use that to help find a general place where our branches are. The other things that we need to look at are x-intercepts. Those are things that make the numerator equal 0. We'll also look at the y-intercept. Basically, you just plug in a 0 for the x and you find what that y value is. And then we're also going to look at domain and range. We're going to use interval notation to write the domain and range, so be sure you remember interval notation from some of the earlier things. Some rational functions also have something called a hole. This is a place where the graph does not exist. So this is in the case where there's a factor that's on the top and on the bottom that are the same. And we can cancel these out to make our graphing a little bit easier. However, we still can't ignore the fact that we did that work. So these are a lot of different parts. I know you're going, oh my god, I have to find all those. They're not that hard to find. So let's look at an example and let's make this graph based on all of these things. So here's the one we're going to graph. I know it looks a little bit scary right now, but once we get it into factored form, we're going to be able to find all of those parts that we were looking for. So if we're going to factor this one, we're going to look at the top, the numerator. I'm going to think, okay, what multiplies to be negative 2 and adds to be negative 1? In this case, it's going to be x minus 2 and x plus 1. Now we look at the denominator and we go, okay, what multiplies to be negative 5 and adds to be negative 4? Well, that is going to be x minus 5 and x plus 1. So you can see that we have a common factor in this one. We can cancel out these common factors, and what we will actually be looking at is the graph of x minus 2 over x minus 5. However, don't forget about these guys. We're going to use them to help us find something in just a second. So looking at the graph that we have, the y equals x minus 2 over x minus 5, there's a few things that we can find right away. The first thing I'm going to find is the vertical asymptote. The vertical asymptote is the place or the number that makes the denominator equal to 0. So if the denominator is x minus 5, the number that's going to make it equal to 0 is 5. So our vertical asymptote is the vertical line x equals 5. I'm going to draw that on my graph. We can also talk about the end behavior asymptote at this point. There is a long, fun way to put this graph or this function into transformation form, and that helps you really see what the end behavior asymptote is. However, if you don't want to do this, there is a shortcut. I don't really like shortcuts usually, but I'm going to use it in this case. It has to do with the ratio of the leading coefficient in the numerator over the leading coefficient in the denominator. Since these both have the same degree, I end up with 1x over 1x, so it's 1. So my end behavior asymptote is the line y equals 1. I'm going to draw that in too. Alright, well now let's talk about the x-intercepts, the things that make the numerator equal to 0. the numerator is x minus 2. The number that makes the numerator equal 0 is 2. So the x-intercept is 2, 0. I'm going to go ahead and graph this too. You can sort of start to see that where one of the branches is going to be. It's going to be in that bottom left-hand quadrant, sort of like the third quadrant. All right, we have a couple more points that we need to think about. We need to think about the y-intercept. The y-intercept is going to be the point that occurs when all of the x's are 0. I'm going to go back up to the function. I would have 0 minus 2 over 0 minus 5. So what I would end up with negative 2 over negative 5, which is 2/5. So the y-intercept is 0, 2/5. Now if we look at our graph, we can see that makes sense. However, that only helps us out on that one part of the branch. So we're going to need to think about the second part. Last but not least, we need to go to those factors that we canceled out. And that's going to tell us that there's a hole in this graph because we canceled some stuff out. The x-coordinate of the hole is easy to find. It's whatever makes the factor we canceled out equal to 0. So in this case, the hole has an x value of negative 1. How do you find the y value? Well, you plug it into your function. You can plug it into the simplified function or the original function. It really doesn't matter. I like the simplified function, so I'm going to do that. I would have negative 1 minus 2 over negative 1 minus 5, which gets me negative 3 over negative 6, which is 1/2. So I have a hole at the point negative 1, 1/2. Negative 1, 1/2. There's my hole. Your hole is going to be an open circle because it is not included in that part of the graph. So I can see that one branch is down here. To find the other branch, you could plug in a test point. I'm going to plug in the test point 6. If I plug in 6, I'm going to end up with 6 minus 2 over 6 minus 5. Well, that gets me 4 over 1. So I know that this point 6, 4 is also a branch, and then I can draw the whole thing because I know which quadrant it's going to end up in. So now we're ready to do the domain and range. We've done the graph. We're done graphing. Yay! Congratulations. So our domain, well, that just means all of the x values. Our x values start here with an arrow, so they start at negative infinity. We use a parentheses for that. The graph continues on until the hole. It stops at the hole, so I need to take that out. It starts again after the hole, continues until that vertical asymptote at 5, and then, I'm running out of space, I'll write over my other stuff. It starts up again right after the vertical asymptote and goes to infinity. So that's our domain. We can also do the range. Typically you're not asked for the range, but let's go ahead and do the range in this case anyways. So the range, again, it starts with an arrow, so it's going to start at negative infinity. It goes all the way up until the hole. It takes a break at the hole, and the y value of the hole is 1/2. Then we start up again after the hole and go to the end behavior asymptote, which is 1. Then we start again after that end behavior asymptote, and we go to infinity. So like I said, it's really not that bad. It's just there's a lot of different parts to it. Once you get the hang of it, it'll go really quickly for you. So now we're going to graph y equals 2x plus 5 over x minus 1. Handily enough, we do not have to factor this one. So we can go ahead and start finding our stuff. We know the vertical asymptote is going to be what makes the denominator equal to 0. So in this case, x minus 1 is the denominator. So the value that makes it equal to 0 is 1. So x equals 1 is going to get us our vertical asymptote. Next, we're going to look at the end behavior asymptote. If the degrees of the numerator and the denominator are the same, it's just the ratio of the leading coefficients. So in this case, I have a leading coefficient of 2 and a leading coefficient of 1. So the end behavior asymptote is at 2. So we have a line at y equals 2. Cool. Now we can move on to our x-intercept. X-intercept is the number that makes the numerator equal to 0. So this is a little bit trickier because the numerator is 2x plus 5. We want to find what makes it equal 0. We're actually going to solve an equation. Subtract 5 from both sides, you can get 2x equals negative 5. Divide both sides by 2. You get x equals negative 5 halves. So my x-intercept is going to be at negative 5 halves and 0. So if we look over at our graph, negative 5 halves is about negative 2.5. I'm going to put my point right there. Y-intercept is where all of the x's are 0. So we just evaluate that. And I'm going to evaluate it from the start. If all the x's are equal to 0, I'm going to have 0 plus 5 over 0 minus 1. So I have 5 over negative 1, which is negative 5. So my y-intercept is going to be 0, negative 5. I'm going to go ahead and plot that on my graph too. Makes sense that it's down there because we can see that that whole branch is down there. Now, we didn't factor anything, and we didn't cancel out any factors, so there are no holes in this problem. We don't have to worry about that. I can go ahead and graph one of my branches, actually. I have enough information to graph that one. I need to know where the second branch is, though. Now, I'm going to do this again by using a test point. So the test point I'm going to choose is 2, because that would be over on the other side of the vertical asymptote. So I would end up with 2 times 2 plus 5 over 2 minus 1. So I would end up with 9 over 1. So the point 2, 9 is the point on the graph. That helps you see where your other branch is, and you can go ahead and sketch that branch. Again, we're not making perfect graphs here. We just really want to get a feel for the general shape. Now that we have our graph done, we can go ahead and do our domain and range. So our domain has that arrow again, so I'm going to start at negative infinity. No holes to worry about, so I can go up to the vertical asymptote at 1. Start up again after the vertical asymptote and go to infinity. The range will be pretty much the same kind of thing too. We start at negative infinity. We go up to our end behavior asymptote. And we start up again after our end behavior asymptote. Done. Congratulations. Now let's try graphing y equals 5x plus 5 over x plus 3. Even though this one looks a little bit simpler, we can actually factor it a little bit further. I'm going to factor the 5 out of the numerator. And that's all I can do to factor it, but that helps me out a little bit when I'm finding all of my things. I need the vertical asymptote, I need the end behavior asymptote, I need the x-intercepts, I need the y-intercepts, and holes, if we have any holes, and we need the domain and range. Now that I have everything all factored, these things are relatively easy to find. The vertical asymptote is going to be the number that makes the denominator equal to 0. If x plus 3 is the denominator, my vertical asymptote is at x equals negative 3. Because you can't divide by 0. We have to take that out. That's why the vertical asymptote behaves the way it does. Now my end behavior asymptote is, if the degrees are the same, is the ratio of the leading coefficients. So in this case, my leading coefficients are 5 and 1. So my end behavior asymptote is at y equals 5. If you were to put this in transformation form, you would see that the graph has been shifted to the left 3 and up 5. X-intercept. X-intercept is going to be the place that makes the numerator equal to 0. I have the factor x plus 1 in my numerator, so that means my x-intercept is going to be at negative 1. I'm going to go ahead and put that on my graph. Now the y-intercept. The y-intercept, we just need to evaluate the function when x is 0. So we have 5 times 0 plus 1 over 0 plus 3. That works out to be just 5 over 3. So 5/3, or 0 5/3, is going to be the y-intercept. I'm going to graph that. Totally messed up my color scheme. That's okay. 5/3 is just under 2. So that actually kind of looks like it fits with the x-intercept I had. There aren't any holes, so that's not applicable. Now we can go ahead and draw that first branch. To figure out where the second branch is, we need to choose a test point. I'm going to choose the test point -4. It's on the other side of the vertical asymptote. So if we were to plug in a -4, we would have 5 times -4 plus 1 over -4 plus 3. Well, that would be 5 times -3 over -1, -15 over -1, which is 15. So that tells me that the point -4, 15 is on my graph, which is way up at the top somewhere. Which just, all I needed that for was to figure out where my branch went, which quadrant it went in. In this case, it goes in that top quadrant there. Alright, we're down to domain and range. Again, it starts at -infinity. No holes, so it goes up to the vertical asymptote. Starts over again after that, and continues to infinity. The range again is similar. I wrote -5. Why didn't anybody say anything to me? It's -3. The 5 is the end behavior asymptote. That's what I need for my range. Alright, and we're done. We found all of the important information and we were able to sketch our graph. This rational is one that we're going to have to factor. So let's go ahead and do that. We are looking in the numerator for something that multiplies to be -2 and adds to be 1. So that works out to be x plus 2 and x minus 1. Then in the denominator, we're looking for things that multiply to be +2 and add to be -3. So we're looking at x minus 2 and x minus 1. So I can see that in this case I'm going to have a hole. My hole is going to be when x is 1. I'm going to go ahead and write my simplified function because I'll use that to find a lot of my stuff. My simplified function is x plus 2 over x minus 2. Alright, so let's go ahead and find our stuff. The vertical asymptote, that would be what makes the bottom, or the denominator, equal to 0. So in this case it's x equals 2. End behavior asymptote is the ratio of the leading coefficients. I have 1x over 1x. So that leaves me with an end behavior asymptote of y equals 1. X-intercepts, where the numerator is 0. So since the numerator is x plus 2, my x-intercept is going to be at -2, 0. Y-intercepts, plug in a 0 for all your x's. So you get 0 plus 2 over 0 minus 2. We end up with 2 over -2, which is -1. So 0, -1 is my y-intercept, which makes sense. Obviously, I can see where one of my branches is going to be. Now, in this case, we do have a hole. We have a hole when x is 1. Now, we need to find the y value of that hole so that we can properly graph the hole. So I'm going to use my simplified function again. I'm going to go, okay, x is 1, which means I have 1 plus 2 over 1 minus 2, which means I have 3 over -1, which is -3. So remember, when you graph your hole at 1, -3, there it is. I need to use an open circle because the graph does not exist at that point. That would be something that would make a denominator equal to 0, and that doesn't exist. Now I obviously can see where one of my branches are. I need to find the second branch though. So to find the next branch, I'm going to plug in a test point. I'm going to choose 3. So 3 plus 2 over 3 minus 2 is 5 over 1. So I know that the point 3, 5 is on my graph, and that helps me see where my second branch is. Again, it doesn't have to be perfect. We're looking for the general shape. Now that we have these things, we can do our domain and range. We have to be careful about the hole in this case, though. Yes, we start at negative infinity for the domain. However, we stop when x is 1 because it's the hole. It's like a point plucked out of the graph. We start up again after the hole, and we go up to that vertical asymptote at 2. Then we start up again after the vertical asymptote and go to infinity. The range is going to be similar. You start at negative infinity. You go up to the hole. That's not there. The graph doesn't exist at negative 3. So we got to start up again on the other side of negative 3. Go up to the end behavior asymptote, which is 1. Then start up again after that. The rest of the examples that I'm going to do in this presentation are just more of the same. So if you think you have a handle on this, you can probably move on to some of your practice. But it might be a good idea to see a couple more, especially because we might need some reminders about factoring. So like I said, I'm just going to be doing a lot of examples. So here's our next example, and it is one that needs to be factored. For the numerator, we need to think what multiplies to be 4 and adds to be 5. That would be 4 and 1. So I have x plus 4, and I have x plus 1. In the denominator, we need to think, okay, what multiplies to be negative 12 but adds to be positive 1, and that's going to be x minus 3 and x plus 4. Ha! So we can see we have a hole in this case when x is negative 4. I'm going to go ahead and write that simplified fraction, though, because it's going to help us find a lot of our stuff. What we're going to be graphing, besides the hole, is y equals x plus 1 over x minus 3. So now let's find our stuff. The denominator equals 0 at 3, so that means my vertical asymptote is at x equals 3. End behavior asymptote. The degrees are the same, so it's 1 over 1 in this case for my leading coefficients. My end behavior asymptote is y equals 1. X-intercept is when the numerator equals to 0. And in this case, that would be negative 1. So negative 1, 0 is my x-intercept. Y-intercept, well, that's plugging in a 0 for all your x's. So you have 0 plus 1 over 0 minus 3. So our y-intercept is negative 1/3. Again, that looks like it kind of makes sense based on where that x-intercept is. Now we need to do our hole. In this case, the hole is going to be when x is negative 4. And again, you need to plug it in order to find the other coordinate of the hole. So I have negative 4 plus 1 over negative 4 minus 3, which is negative 3 over negative 7, which is positive 3/7. Now, just leave it as a fraction. Remember, we're estimating it. 3/7 is smaller than 1, so negative 4 and 3/7 will be somewhere underneath that vertical asymptote, in between the x-axis and the end behavior asymptote. Now I obviously have enough to graph one branch. That's a hole, I swear. It's a big open circle. Open. Alright, and I need to choose a test point in order to find the other branch. I'm going to choose 4. I'm always choosing the smallest number possible on the other side of the vertical asymptote. Makes your calculations easier. So 4 plus 1 over 4 minus 3 is 5 over 1. So 4, 5 is one of our points. And that helps you see where the second branch is. You can go ahead and sketch that in. Now that we have everything graphed, our graph is done. We just can write the domain and range based on the graph. We start at negative infinity. We stop at the hole, negative 4. We start up again on the other side of the hole, and we go to the vertical asymptote at 3. We start up again on the other side of the vertical asymptote, and we go to infinity. The range, again, starts at negative infinity. goes all the way up to the whole at 3/7. Starts up again right after the 3/7, but just for a little bit, because we stop again at 1. Then we start up again after that, and we go to infinity. Yay, we get to factor some more. I love factoring. I know you guys love factoring too. When we look at the numerator, it actually has a leading coefficient of 2. So this is a problem you might want to do with factor by grouping. Now I'm not going to go into all of that here, so you might want to pause the video, try to factor it yourself, and then come back to it. The denominator, I know you guys can factor the denominator. What multiplies to be positive 6 and adds to be negative 5 is x minus 2 and x minus 3. The numerator is a little bit trickier. If you want to use factor by grouping, please do. I'm going to do a little shortcut with a little bit of guess and check. We need negative 3 and we need negative 5, so that would be 3 and that would be 1. Alright, I got it factored. Is there anything we can cancel out? Yes, there is something we can cancel out. So that means we have a whole. We can cancel out the x minus 3, so we have a whole at 3. I'm going to go ahead and rewrite my simplified fraction so I can figure out what's going on. And let's go ahead and find our stuff. Vertical asymptote, number that makes the denominator equal to 0 is 2. So our vertical asymptote is y equals 2. Sorry, x equals 2. Now we need to do our end behavior asymptote. So we're going to look at the ratio of the leading coefficients. In this case I have 2 over 1. So I have a end behavior asymptote at y equals 2. X-intercept, number that makes the numerator equal to 0. Be careful about this one, because the numerator is 2x plus 1. If that equals 0, it's definitely not just going to be negative 1. You have to solve that equation. Looks like our x-intercept is going to be at negative 1/2. Oh, I've ruined my color scheme again. Oh well. So negative 1/2, 0 is our x-intercept. That's where it crosses the x-axis. The y-intercept is when you plug in a 0 for everything. So that would be 2 times 0 plus 1 over 0 minus 2. So that would be 1 over negative 2. So our y-intercept is also at negative 1/2. But remember, it's a different point. It's 0, negative 1/2. So it's not like they're at the same place. I swear that's at negative 1/2. Holes. We do have a hole. We have a hole when x is 3 because that's what would make the factor we canceled out equal to 0. Now we have to plug it in. So 2 times 3 plus 1 over 3 minus 2 will get us the y value of the hole. So that leaves me with 6 plus 1, which is 7, over 3 minus 2, which is 1. So I have a hole at 3, 7. I'm going to go ahead and graph 3, 7. This is actually kind of awesome because we have both of our branches. We don't need a test point. We know that one branch is going to be down here. We know that the other branch is going to be in the top corner there. Again, we're just sketching the graph. As long as we have a point of the branch, we know where the branch is overall. Now we can go ahead and do our domain and range. This one's going to be a little bit different because our hole is in a different place. Start up at negative infinity, and I don't stop again on the x-axis until the vertical asymptote. Start again after the vertical asymptote, but stop right away at the hole. Start up again after the hole, and continue to infinity. Now for our range, bottom to top. We go from negative infinity all the way up to the end behavior asymptote. Then we have to start up again right after that. We stop at the y value of the hole. Start up again after the hole and continue to infinity. Good job. You guys are graphing all this nonsense and finding all of this. So, like I said, it's not that they're really, really hard. It's just there's a lot of components to it. And again, practicing makes it oh so much easier Because once you have that skill built in, your little mind and your hands, remember it, can find these things really fast. So just to do a little recap, the very first thing you need to do is factor everything. Obviously, you have to have factors in order to graph, to find all the attributes that you're going to graph. Remember that numbers that make the denominator equal to 0 are the vertical asymptotes. Numbers that make the numerator equal to 0 are the x-intercepts. Factors that occur in the numerator and in the denominator that cancel, those represent wholes. So these are the ones that you can cancel from the top and the bottom of a fraction. The end behavior asymptote, the EBA, can be found using the ratio of the leading coefficients if the degrees are the same. If the bottom is bigger, the EBA is 0. We'll look at some examples in the next graphing rationals video where you see that happen. So that's it. You just have to remember, find all of those things, and you're well on your way to graphing all sorts of wonderful rational functions. Hooray!